Okay, continuing what we've been working on, I'm going to eliminate the parameter, but here I'm dealing with cosine and sine now. Okay, remember this looks a lot like x equals r cosine theta, y equals r sine theta. Remember we see that in the unit circle. This is not a unit circle, but as we pretend it is, if it goes around, you know, x was always r cosine theta and our y was always r sine theta. If you graph this in your calculator with parametric mode, you'll come up with a circle. The center's at the origin, the radius is 2. Okay? So we know with the equation, so we want to get rid of the t and get it back into y equals. It's called eliminating the parameter. So here's a trig identity. It's something you just need to know. Cosine squared of theta, or t, plus sine squared of theta equals 1. That's just a rule, an identity, or a theorem. Okay, and I call it an identity in trigonometry. All right. That being said, if we graph this parametric, we know we've got a circle. So we also know what's a circle in without parametric mode is x squared plus y squared equals your radius squared. So we know that x squared plus y squared equals this right. Well, what is our equals? Well, first of all, let's just say what's x? X is 2 cosine t. So x squared plus y squared equals, let's plug this in for x, 2 cosine t squared plus 2 sine t squared. So x squared plus y squared equals 4. 2 squared is 4. And cosine t squared is going to be cosine squared t. You put the square there. Again, 2 squared is 4. Sine t squared is going to be sine squared t. And then we take out this 4. We have 4 is common to both of these terms. So we factor out a 4, and I've got cosine squared t plus sine squared t. And what I say about cosine squared plus sine squared, that's just 1. So 4 times 1 is 4. And there's our equation, x squared plus y squared equals 4. So my radius is 2. Remember, this is r squared. Okay? If you have, remember our formula for circle is x plus, it's always x minus h squared plus y minus k squared equals radius squared, and our center is hk. Okay? So if you have a circle with radius equals, let's say 3, and the center of the circle is at, let's say, 3, 2, okay? In parametric mode, I'm going to have 3, that's my x component, plus my r cosine theta, which is going to be, my radius is 3 cosine t, and then since this is my center of my circle, here's the center. It's not the origin. It's at 3, if you can see that, 3, 2. So I'll take my y component now, and that's going to be 2 plus r sine theta, which is going to be radius 3 sine theta. Okay? And that'll be the parametric mode for a circle with a center of 3, 2, radius 3. Okay? So if it was at the origin, it would just be this, 3 cosine theta, 3 sine theta, or t. But since the center is not the origin, it's at 3, 2. 3, that's a 3, 2. It's 3 plus that and 2 plus this, okay? Okay, next, we're going to have real world problems dealing with, we're going to break down parametric equations for motion, and golf balls, baseballs. In this case, I have a baseball batter here. He's going to hit the ball. This is at 3 feet above the ground, and the ball's going to be hit at 18 degrees at 150 feet per second. Okay? And the wall of the baseball stadium is at 400 feet, and it's 20 feet high. Okay, will the ball make it out? Okay, so we want to break things up. First of all, remember I'm just talking initial now. The initial velocity of this ball, the horizontal will be, this is kind of my vector, right? It's going to have 150 as my component this direction. So the horizontal component is going to be r, or in this case magnitude times cosine of 18, or in this case the initial velocity cosine theta is the x component. The y component, the initial y component, is this initial velocity times the sine of theta. Okay, but we're dealing with gravity now. So the y equation in our parametric equation is going to deal with the physics gravity, where you've got negative 1/2 gravity times time squared plus the initial velocity times t plus the initial height. The zero or the naught is the initial velocity, and that's for initial height. Okay, so let's just talk about x sub t. My x, my parametric equation, my x is a function of t equals my initial velocity v times cosine of theta and times time. Okay, so that's going to be 150 times cosine of 18 degrees times time. Okay, all right. That's what its vector's at. It's vector, and for how long does it go? Because this is going for this is in feet per second times seconds, and leave us in feet. Okay. Now the y component, that's where this vertical track of the ball, where if we plotted the y, it's subject to gravity. It just doesn't keep going higher and higher and higher. So we use this equation here. So the negative 1/2, we're using the gravity is going to be not in meters, but either 32 feet per second. So half of 32 is 16, and it's negative. So it's going to be negative 16t squared, okay, plus the initial velocity 150 times sine of 18 degrees t, okay, times the t, plus the 3 feet, which is our initial height, okay? And from here, we can use the calculator. We can see if we clear if we get a home run or it hits the wall, or if it's catchable, okay? So one thing you can do without using the calculator is, this is just for the horizontal distance. Well, we know that what I'll do first is I'll set my horizontal distance to 400 feet, okay? And that equals 150 cosine 18 times time. 150 cosine 18 degrees times time, okay? So if I divide both sides, I can get the time it takes to hit that 400 feet, okay? So 400 divided by 150 cosine 18 degrees equals time, okay? Once we get that time, I can go back into this equation and plug in that time and find out the altitude. Does it clear the wall or doesn't it, okay? And we can do more with the calculator, okay? Okay, so the next thing real quick I'm going to try to work through is a Ferris wheel problem. Okay, here's a Ferris wheel problem. We've got this person, let's say it's Jenny. She's right here at the 3 o'clock position, or like where we start off 0 pi and so on. And this thing rotates at a revolution per 10 seconds. So 2 pi per 10 seconds. That's an angular velocity, right? 2 pi per 10 seconds. Let's get what we call a unit rate. What's 2 over 10 is 1/5 pi per second, okay? All right, so 1/5 pi is our rate, okay, of this thing rotating, okay? Remember, here's our Ferris wheel. It's got a radius of 30 feet, and this platform is 10. So remember, anytime we have a position on the unit circle, x is going to be r cosine theta. In this case, we'll start off with theta. Okay? And our y is going to be, we have an initial altitude of 10, plus r sine theta. So basically I've got x sub t equals 30, which is the radius of the Ferris wheel, times cosine of theta. Y equals the initial 10 plus 30 sine of theta. And here's the only trick. Theta deals, we have to figure what, like I said, the rate comes in. Like we said, it was given in the problem that it's 1 revolution per 10 seconds. So really theta is going to be a function of time, where this is a parametric equation. We have to have a t in here. So I'm going to change x sub t equals 30 times cosine of pi over 5 times t. Okay, so that's really what theta is going to be. After so many seconds, we're going at pi fifths per second. So how many seconds we go, that tells us how much of an angle we swept through. So that's really our theta. It's dictated by what t is. If t is 2, we go 2/5 pi. Okay, if t is 3, it's 3/5 pi. Okay, and then y equals 10 plus sine of, again, pi fifths times t. And that all came from this initial 2 pi per 10 seconds, which is 1/5 pi per second. Okay? They want to know where they're going to be at 22 seconds. You can just plug that in. At 22 seconds, 30 cosine of 22 pi over 5, and do 10 plus sine of plugging in 22. And you can get an x, y coordinate. And we'll do some problems on this Tuesday. All right? Thanks, guys.